this morning it's going to be a brief introduction to two things. First of all, Monte Carlo, random walks, and then I'll stop and then I'll have a brief introduction to variational Monte Carlo. And because in getting ready for the lab session this afternoon on variational Monte Carlo. So this is the first lecture is random walks, Monte Carlo, and errors. And so first, this is the key paper in the field that introduced the field, the famous paper Metropolis. And interesting story here. Of course, we call it often Metropolis method or Markov chain Monte Carlo. But you notice there are other authors on this paper that if you go back in history, you find that actually the method, Metropolis was not the main person that developed this method. It was mainly developed by a husband and wife team, the Rosenbluths, and Edward Teller, the so-called inventor of the hydrogen bomb, was the key guy that poked them into doing the work. But Metropolis was first in the alphabet, and he was also director of the lab that owned the computer. So we call it Metropolis method. 1953. And it's interesting that they did a number of things on this computer in Los Alamos in 1950, and many of them have become entire fields of science, like Monte Carlo. Another thing, they did the first CFD, computational fluid dynamics calculation, the first scattering types of calculations, and so forth. It shows that when you develop a new instrument, you can do lots of new things. So I want to describe a little bit about this Monte Carlo method because all types of quantum Monte Carlo are based on this type of algorithm. It's quite simple though. So I call it, I'm not sure Markov would be any better inventor as a field, although it's much earlier, but a Markov chain Monte Carlo, basically, it's a random walk through some sort of phase space. And the different types of quantum Monte Carlo or classical Monte Carlo differ in what the phase space is, but basically it describes the state of your system. And in most of our quantum Monte Carlo, the state of the system are just the electron coordinates. So we put in electrons in a box of some kind, periodic box, and the state of the system are the 3n coordinates, XYZ coordinates of those n electrons. And so, you know, they move around according to various rules, and you do different things, and that's the Markov process. So Markov means that the definition is you move S, so S1 is the state of the system. Of course, on a computer, it's always a discrete distribution. That is, you have a certain number of bits that describe it, right? And then you have a rule that changes it from S1 to S2. And it's a random walk, meaning that you have a probability distribution, a so-called stochastic matrix. So you have if you're at position Sn, what is the probability that you go to Sn plus 1, a new point in phase space? It's a matrix because these are discrete, so it's like a very high dimensional matrix that you sample. But it's a stochastic matrix. That means it has these two properties, namely that it's a non-negative because it's a probability, and it's normalized in this way. That is, if you're the probability of going somewhere else is 1, right? You just don't. We see that when we do diffusion Monte Carlo, in a way we break this rule, but we have a more general rule. But in what we're talking about today in variational Monte Carlo, we have this rule that is, you know, the random walk doesn't die or create new walks. The probability is 1 that you have the walk at the next step. So if you sum over the outcomes, you get 1. And the definition of the Markov chain is that this probability only depends on where you are now. It doesn't, it also has to be probabilistic. That is, it's not deterministic. That is, there is some random element of where you go. That's where it differs from molecular dynamics. If you know molecular dynamics is F equals ma, classical dynamics, and that's a deterministic equation. It's true that in molecular dynamics, where you are in the next step only depends where you are now, but there's no element of probability there. There's no randomness. And so therefore, in a deterministic algorithm, it's much more difficult to prove what the stationary state is. That's the whole problem in statistical mechanics. But in this Markov process, where this is actually a probability, then we can write down the evolution of the system in a matrix form in a very simple fashion. If we say f of n is the probability that after n steps we're at a position s, then what is the master equation? How does that evolve in time? And so this is the so-called master equation. That is f of n plus 1 is this matrix times this f of n, essentially. And it's just a matrix vector product in a computer, right? But we can't do it in a computer because our state space is so large. We have to do it by actually sampling, doing the simulation, right? Just imagine if you had n electrons and say you had a space that you could discretize into, say, 1,000 elements in your box. Well, if you have n electrons, then you would have 1,000 to the nth power of ways you could put the electron in the box, and that would be f of n, would be a vector that would be 1,000 to the n elements, and your matrix would be that squared. So you can't hold that in the memory of a computer. So now instead, what we do is we actually carry out this random walk. We do kind of the opposite of what you learn in theory. Theory, you would say, we have a random walk, and then we try to model it as an eigenvalue problem and solve it with some basis. But here, we have an eigenvalue problem, and we model it by a random walk, and we use the random walk on the computer, right? So what are the stationary states of this distribution? Well, that's an eigenvalue problem here. And then there's some theorems that Markov proved in some cases. And the main concept here is ergodicity. Ergodicity, in a way, means that you can go everywhere in your space. And often I give, this is called a drunkard's walk. So you imagine some students in this town, Champaign, Urbana, walking around on Saturday night. Every time they come to a corner, they forgot where they're going, and they go north, south, east, or west at random. And then, so the random walk, is where they end up after, at sunrise or something like that, right? And ergodicity would be, there's no impediments to going anywhere in town. There's not like a road closed or a fence or something like that. They can move everywhere, and so that gives you some idea of, then you can prove what the distribution is going to be at the end of the day, right? And so these are some of the characteristics of ergodicity. After a certain time, the system loses memory of its initial state. There could be conserved quantities, but we don't have to concern ourselves with that now. In which case, well, for example, a conserved quantity on this problem I just mentioned about the drunkard's walk, I mean, there is a parity, for example, if you have like a perfect square grid and you have even sites and odd sites, and you could say after an even number of steps, it's always on an even site. That would be an example of a conserved quantity. But you don't usually have that in the type of work we're going to be doing. Now, so there is a correlation time, which we're going to define in about a half an hour or so, is the number of iterations it takes to forget where you started. How many steps does it take? So again, in this example of students walking around town, suppose the town was finite, they never go out into the countryside, then how long does it take for them sort of to go from one point to another point? How many steps does it take? That would be the correlation time. So we use the ergodicity essentially for two reasons. And this is important in the Monte Carlo. There's always a warm-up period at the beginning of a random walk. So you do a simulation, path integrals, variational Monte Carlo, diffusion Monte Carlo. You start the system out in a certain state, and then you go for equilibration time, and then you throw away those results. That's called the equilibration or warm-up time. Okay, that's an important practical issue. And the second is when computing error bars, and we're going to come to that in a few minutes, you need to get an idea of when samples become independent. If it takes forever, if it takes like a whole day on the computer to get independent samples, then it's really hard to know if you've converged or not. So here is the famous Metropolis algorithm, and the key thing that they introduced, that Metropolis, Rosenbluth, and Teller introduced, is the idea of rejections, this third state here. And basically, what had been known in statistical mechanics before that was this idea of detail balance. Pi of s is the distribution that we want to sample. For example, in variational Monte Carlo, would be the square of the wave function. P of s, I've already told you about, is the rule that tells you to move from s to s prime. And detail balance is a condition that the rate going one way is equal to the rate going the other way. And you can prove that if you have detail balance, if you have this equation between all states s and s prime, then pi of s has to be, if it's ergodic, has to be the unique equilibrium configuration. So Metropolis provides you with an algorithm to sample any probability distribution in a good way. So that's the result. If P is ergodic, pi is a unique steady-state solution. And the Metropolis achieves this detail balance by rejecting moves. This is an example I'm going to use for a few minutes, the classical Boltzmann distribution, which I hope you remember from statistical mechanics. This is the distribution in classical mechanics. H of s is some energy functional for the configuration. In beta is 1 over the temperature. Inverse temperature, and z is just a normalization factor called the partition function. So basically, in the Metropolis procedure, this is the rule for moving from s to s prime, and we divide it into two parts. One is the probability of an attempting a move, t of s to s prime, and I'll give you an example in a minute. And then A is the probability of accepting that move. And then we require detail balance on this, and this is an equation that we use in Metropolis to actually accept the move. So A is determined by this transition probability and the distribution that you want to sample, this pi of s prime. This is the Metropolis acceptance ratio. So I'll show you how this comes about on the algorithm, but it's a couple minutes work of algebra to show that if you have this funny looking formula for the acceptance probability, then it satisfies this detail balance equation that I gave you a minute ago. That's where it comes from. And this is, you can show the sort of best formula for the acceptance probability in Metropolis. So here is applying this to the Boltzmann distribution, the classical Boltzmann distribution. Here is written down the acceptance, and here actually I have a figure here. Okay, so here is a classical system. This is a box, and this is where the particles are at some stage of the random walk. So this is where those blue dots are is the state of the system. Oops, I forgot to convert a symbol. This is supposed to be delta, which is the step size. Okay, and so we make a move. Like we move this particle, we pick this particle at random from all these particles, we move it to this new position here, this orange dot, and so that's what this formula is. And Spring is actually a random number generator, which we developed here a number of years ago, so I just use that as a call. In any computer language, or a library, you have a random number generator that generates numbers between 0 and 1. Okay, and so I'm not going to talk about that very much, although there's a lot to say. But anyway, so spring minus a half will generate something between minus a half and plus a half, and this really should be a vector, so you have you do the same in x and y. So you sample everything inside this black box here, and then delta is the size of the box, right? Because this is between 1/2 and minus 1/2, and so delta makes it between delta over 2 and minus delta over 2. So the new coordinates are equal to the old coordinates. Then you compute the energy for this new state. And here's an example where you have a pair potential, like a Lennard-Jones potential or a Coulomb interactions, V of R. And you calculate, this is the new coordinate, that's the old coordinate, and you calculate how the energy changes between the new coordinate and the old coordinate. And then this is the acceptance probability. And I was showing you here, this is the acceptance probability. This somehow got out of order. The acceptance probability is this function right here, right? And if it's greater than 1, we accept it. If it's less than 1, we accept it with a probability of less than 1. So if you make a move that goes down in energy, you always accept that move. You always go downhill. But if you go uphill, remember beta is 1 over kt. If you go uphill much greater than kt, you're very likely to reject the move. And so let's see, I covered everything there. And so given ergodicity, ergodicity means in this system that these little blue dots can move everywhere in the box. They can go to every kind of configuration. You see that's obviously true. That is, just imagine these were little marbles or something in a box. You can clearly rearrange these marbles any way you want in a finite number of steps, and so it's ergodic. So you see how simple the proof is that this has to converge to the right answer if you run long enough. The only question is how long do you have to run? So I think I covered that. Okay, so here is a prototype Monte Carlo code, Metropolis Monte Carlo code, and where I'm just summarizing all this in kind of a pseudocode. So, as I said, you have to have a way to initialize the state. That is, put the marbles in the box in some reasonable fashion, right? Not some pathological state, but some reasonable fashion. Okay, and then you have a loop. And this, of course, is the time-consuming part, because this loop could be millions of steps. And it also could be loop over lots of processors. I mean, that's how we do parallel. We'd set off a different random walk on every processor or something like that. But anyway, that's the big loop in the Monte Carlo that takes the time. Each individual step is this. We sample a new coordinate based on the old coordinate, and we have to calculate the probability that we sampled it for. And this 1 means that we're going in the forward direction. And then we calculate the new energy. And we might have to calculate what the probability of going backwards is. That's because in this formula here, we need both a forward probability, that's this, the bottom denominator is the forward probability, and we need the backwards probability too. But very often you don't need this. If these were equal to 1, of course you don't need to know what they were. Okay, and so that's what this step is, find the probability going backwards. Now this is going to be the acceptance probability. This is just that formula I showed you a minute ago. And here, this is the accept to reject step. And if you accept it, if A, this formula here, is greater than the random number, then you decide to accept the move, so you overwrite the old coordinates with the new coordinates. and the old energy with the new energy. And very importantly, you keep track of what your acceptance probability is, because that's the key quantity in a Metropolis thing, is what is the acceptance probability. I'll explain that in a second. But a very important thing is that then you calculate your averages. And you notice this averages is outside of this clause right here. That is, whether the move was accepted or rejected, you count it. So rejected moves count the same as accepted moves. So if you sit there in one configuration for 100 steps rejecting all moves, that step counts 100 times. And this is a common error that you might make in your programming. You might think you're only going to count averages when you move somewhere, but that's not the case. You have to do it according to the theory of Markov chains. Okay, so here you always want to measure the acceptance probability, and here is just actually an example that somebody did in terms of this simple classical system. This is the delta, which is the step size, and this is the probability that you accept the move. And here is actually how you diffuse through phase space. This is the diffusion constant through phase space. It's a function of this delta. And the general theory is you want to move through phase space as fast as you can on every step. And so the general features are, if you make delta too small, of course you don't move through phase space too small. You're just inching along. You're just going along really, really slowly, and you don't move very fast through phase space. However, you can't move arbitrarily far, because if you move too far, this particle that you're moving, you throw it across the box, it's going to land on top of another particle, and that's going to be a rejection, right? So the curve goes down, and so there's an optimal place. And you see that, well, we have different curves here. So here we want to focus on the black dots, which is this curve. And you see the optimal diffusion occurs at a delta of, about 0.3. And looking over here, you see that the acceptance ratio is about 30%. And that's typical. Usually my rule of thumb that I would tell a student is your acceptance ratio should be between 10% and 90%. 10%, that means you're mostly moving and you're throwing out the move. It's not accepted. 90% means you're moving so slowly that of course it's accepted, but you're not going very far. So, somewhere in there. And you see that this curve, 10% and 90% would be, well, a range from 0.2 to 0.4 sort of over here. And the diffusion, of course, it does have a maximum, but it's going to take you longer to find out where that maximum is than you're going to gain in any kind of efficiency. So, you just don't want to be way down in here. The main thing is you always want to look at the acceptance ratio and make sure that it's not zero. Zero acceptance ratio means that you have not moved the random walk from the beginning of the code, and you're obviously not doing anything. So you always have to put that in your code, and you always have to look at it, or put something in that says to stop if you're doing that, right? Okay, the second topic now is how you estimate errors. This is the rule here. Without error bars in Monte Carlo, your results are completely useless. I mean, that's the general rule in science, right? You have to know how significant the results are. I mean, it doesn't apply to something like DFT because there's no real way of calculating the error bars. You have a numerical precision, which you can make really, really small, but then this important thing like what's the effect of the functional, the pseudopotential, there's no really easy way to do that anyway besides looking at a lot of different systems or something. But that's not true in Monte Carlo. In Monte Carlo, there's always a very simple way of calculating error bars, and you always have to do it, right? If you come to me and you say, oh, my results are 2.1, and I should have been getting 2, it doesn't do anything for me. It's like, well, If the error bar is 0.1, this is completely normal, right? The error bar is 0.001, then you have a problem. So until I know what the delta divided by the error bar is, I don't know whether the result is worth worrying about or not. So in what sense do we calculate exact properties? The answer is if we average long enough, the error goes to 0, and so you can control the errors in the simulation. The second rule is there's as I said, there's always a very simple way of estimating errors. And now that we have parallel computers so easily available, the simple way is the following. Just run your code on 4 different processors and look how it differs from one run to the other. Does it differ in the 2nd decimal place or the 3rd decimal place? And of course, the error estimate is not very precise, but it's better than no error estimate. This is kind of the eyeball estimate. Of course, when you do that, there's a very easy mistake that you can make. Namely, you have to make sure that the seed of the random number is different on those 4 different computers. Otherwise, of course, you'll get exactly the computers do what they're supposed to do. Namely, they execute the same pseudo-random number sequence if they have the same seed and generator. So by the error bar, we mean the estimated error and the estimated mean. And I'm going to talk about this a bit more. This is what I call the trace of the energy. This is the iteration count over here. So this is a run that had about 5,000 steps. And here is this initial part, which was caused by the startup. You know, I started up the run with an energy up here, and it came down, and then it fluctuates like this forever, right? That's normal. These are just the fluctuations. And the idea is that the mean value, of course, you average, you throw out this part, and then you average over here. And there's this is a histogram of the fluctuations. Jeanne, are we planning to use Dataspork? Okay. Okay, so this is coming out of this Dataspork program that's these graphs. And this shows you the histogram of the number. And okay, so the mean value you always understand as this. And so the question is, what is the error of the mean? And I'm not sure I can see it on here, but on some of the other graphs we can see it. But an eyeball estimate would be what is the of the error bar on the mean? Well, there's 2 ingredients that come in there of the error bar. The fluctuations in the energy, and you can see that they're on the order of less than 0.05, the fluctuations, divided by the square root of the number of independent measurements. And that's a little hard to estimate. But what you see in here is it's not 5,000. That's not the number of independent measurements. That's the number of steps of the random walk. And the reason why it's not is because there's correlation between these measurements. Because your random walk is moving rather slowly through phase space, it takes a number of steps to become decorrelated. And you look at a feature like this right here. You see the energy goes up and then it comes down. And so how many times does it go up and down through here? Well, I would say maybe about 20 or 30 times during this whole run. I can tell you precisely, I can calculate it, but eyeball estimate. So the error bar would be something like 0.05 divided by the square root of 30. So, you know, that's going to be a number like 0.01. So the error and the energy would be about 0.01 from here. And so you see, a number of things are important. That is, we looked at this figure. This is another thing that you would want to look at, this so-called trace of the energy to see, what the fluctuations are there any features, and so forth. Okay. There is a very famous theorem, of course, due to Gauss, called the central limit theorem, that says under certain conditions, all error bars go to a Gaussian distribution. I'm not going to go through the proof, but this is the Gaussian distribution. And so given enough averaging, almost anything becomes a Gaussian. Note that I didn't say anything because there are conditions. And in particular, well, here's an example. If we have a square distribution, a random number generator generates a square distribution. If we take two such random numbers and add them together, we get this triangular distribution. If we take 3, we get a quadratic distribution. If we take 4, we get something that looks almost like a Gaussian. So this shows you how quickly adding together random numbers becomes a normal distribution. After 12 of them, you can hardly tell the difference with a Gaussian. And so independent, you see, we had a distribution of energies here. And when we add together all of these things here, we generally get a normal distribution. And the error, the standard error, is given by this coefficient here in the Gaussian. And this is what we mean by error bars, is the standard error. And that means that, you know, if you probably remember from statistics that 2/3 of the time, the correct answer will be within 1 sigma of your estimated answer 2/3 of the time. 90% of the time, it will be within 2 sigmas. Now, when you heard about the Higgs boson being discovered at CERN, they were talking about a 5 sigma effect. So you can figure out what the probability of that being is. So this is what we mean, the central limit theorem. And so, you know, we estimate the error bars and the mean value from the Monte Carlo itself. Here are the conditions on the central limit theorem. And it's mainly this third one that you have to worry about. So suppose we're just doing a simple integral like this, the integral dx of f of x with Monte Carlo, and we have moments of this distribution, x to the n, that's the nth moment. Well, if we're sampling f of x and we're calculating the average value of x, for example, if the 0th moment doesn't exist, well then f is not a probability distribution function, and you know, so you can't use the central limit theorem. If the first moment doesn't exist, the physics question you're trying to answer is not well posed. You haven't written down the right integral to do. But usually when you're doing a physics calculation, you only have to worry about these two things. But in Monte Carlo, you have to worry about the third condition, namely that the variance doesn't exist. And that's the second moment, x squared moment. And it's important to know if the variance is finite for a simulation. This would mean, because if the variance doesn't exist, then the central limit theorem might not hold. And this would be caused by your estimator, the thing you're trying to calculate, having long tails in the distribution, that is having going off to infinity too slowly, for example. I'm not really going to show you an example, but to estimate errors, we use these standard formulas from statistics. That is, we have a time series, n steps in the time series. This is the way we calculate the mean, right? We just take the mean value, and that's our estimate of what the integral is going to be. And then this is how we calculate the error bar, by looking at the fluctuations in A. And you know, you have these factors of n and n minus 1 you have to worry about. Now, these formulas are what you learn in statistics, but you can also work out the formulas if the data is correlated. That is, if, like I was saying before, over here, there's some correlation between the data points, and that's the case in Monte Carlo. It can be correlated. And the difference is we have the same formula here, except for this kappa, this correlation time. And this is what I mentioned in the beginning of the talk. How long does it take for the random walk to forget where it started from? That's kappa. And this is the way it's defined for a property, this property A. It's defined in terms of the autocorrelation of the property with itself at some later time. It's the integral or the sum of the autocorrelation time. And there's essentially two ways of calculating this kappa. One way is a direct way, namely you just do this sum, and I'll show you here. Here is I guess the same data I just showed you before. This is the data sport program that you'll look at today. And here is this autocorrelation function. That is, this function right here is a function of time. That is, what is the fluctuation at one time averaged with the fluctuations at a time t later. That's this little red curve here. And you see it starts out at 1 because a fluctuation is always correlated at the same time by definition. And then it drops down. And then it goes to 0. If it's ergodic, it goes to 0. That is, it forgets where it started from. And this area under this curve is kappa. And that tells you the number. Remember in this example there were 5,000 steps. Now I can actually see what the correlation time was. It's 25.8. Of course, that's an estimate. We'd have to run a lot longer to make that precise. But it doesn't really matter. We don't need it precisely. So we would take 5,000 points and we divide by 25. So that's about 200, 200. And then you take the square root of that, that's 5. And you see that the sigma was 0.02. I said 0.05, but it's 0.02. And so the final error bar is 0.002. That's how we arrive at the error bar. Of course, this is, of course, a dumb computer program. Don't believe all those decimal places. You have to put them there just to make, you're not supposed to, there's an error of the error, but we don't want to get into that. Then you have the mean value. So here's the answer, minus 2.2545. Okay, and all those decimal places after the 4-5 are completely useless, right? You might quote, the error is 0022. So 0022. So it's 45 plus or minus 22. So that means with 2/3 probability, it's like between 0.252 and 0.255, right? That's what you learn from this. Now the other way is the blocking analysis, and that's done down here. And the idea is you take this kind of a cute recursive algorithm. You take these 5,000 data points, throw away the first part, and then you calculate the error bars using this formula here. Then you take neighboring data points and average them together. So instead of having 5,000, you only have 2,500. And then you use this formula again. Then you do it again recursively every time, adding adjacent data points together, right? So you can do this, and you see the correlation time gets divided by 2 each time you do that, because points that were, say, 16 iterations apart, if you add them together, they become 8, and then 4, and then 2. And so that's what's showing here. This is showing the error bar as a function of the number of bisection, or you don't call that bisection, yeah, what do you call it? When you add them together, again, averaging. And so, here they're 2, 4, 8, 16, and so forth. You see the error bar is going up and up and up because you're getting the effects of correlation put in. And so hopefully this would plateau out. But it didn't quite. We didn't have quite enough data here to plateau out. But if you have more data, it would. And so you get an idea that the error bar here is, well, 0.022, which is what we calculated with this correlation time. This thing has another problem here, and that's how you cut off this integral. I told you that the correlation time is the area under this curve, but you can't, you're not supposed to add in all this area here. This is just noise. So a human has to go in and figure out where to cut off the integral. because if you don't cut it off, you just get garbage. So anyway, those are the kind of the problems of estimating the error. But the point is, you have to do something, and the idea is not to get a more precise error estimate here. That would be nice, but that's a hard problem. If you really want a more precise error estimate, you just run this thing 10 times longer. That's the beauty of the Monte Carlo, right? And then everything will get better if it's well posed. Okay, I already explained correlated and uncorrelated data. There's a whole vocabulary of statistics that's very useful. People would use this vocabulary because then otherwise you're talking about the same thing. So the trace of A, that's this curve, these curves right here. That's just showing how things progress in iteration. Okay, equilibration time I explained. The histogram I explained. The mean value and the variance I explained. The estimate of the mean is what you think the average value is. The estimate of the variance is what you think the error bar is. The autocorrelation I explained, the correlation time. Then the estimated error of the estimated mean, that's what you think that the error bar is. And then finally, I didn't explain the efficiency, but the efficiency of a Monte Carlo procedure is how quickly the error bar decreases with computer time. And you can get a better efficiency of your code by making a faster code, by getting a faster computer, or by making a better estimator, and lots of different reasons. Or you have better algorithms, like you can change the step size, and that will make it more efficient. This is the bottom line of the efficiency, just like on a car where we say miles per gallon, right? And it's like, this is the measure of how good you are. And so it's the computer time times this error bar squared, 1 over that. So problems with estimating errors. Any good simulation, you have to quote both the systematic and statistical errors for anything that's important to your conclusion. The error and the mean are simultaneously determined from that same data, and I just explained how. The central limit theorem applies if the variance is finite, and so there you can use the concept of standard deviation. So again, just to mention, it does not matter if the individual distributions, like the energy, are normally distributed. What we mean is that after you average over hundreds of steps, that's normally distributed. The problem in the simulation is that the data is correlated in time. That does not mean that the error bars are not correct. It means you have to account for the errors. You have to figure out what the correlation time is, and you have to make sure that your correlation time is much less than your run time. A good Monte Carlo, if it takes 1,000 steps to become decorrelated, you should be running for 1,000,000 steps, right? Not just 1,000 steps. Otherwise, you don't really know that that's the correlation time. Okay, so anyway, any questions about error bars? Yes?
The formulas for uncorrelated data and correlated data, are they general enough, or are they particular to Monte Carlo? I mean, they look like they should be for any deterministic, stochastic, or stochastic, or even experimenters.
Well, if the assumptions of the experiment or the molecular dynamics are valid, I mean, ergodicity is the key concept here. And molecular dynamics, I don't know about experiment, that's a bit, a lot of things can happen in experiment, but in molecular dynamics, which is deterministic, you do have, not all molecular dynamics is ergodic. The famous Fermi-Ulam-Pasta whole line of reasoning about chaos and so forth, that thing is not ergodic. But we think generally in statistical mechanics that classical dynamics is ergodic, and you can use the formulas. You could get negative correlation times in molecular dynamics, whereas you can't get it in Monte Carlo. That's interesting. But yes, the formulas are general. Any other questions about error bars or Monte Carlo? Yeah?
So here you showed error bar for energies. For other properties, you have to calculate separate error bars? Or is there
Yeah, that's right. He asked me whether other things besides the energy, if you were calculating the pressure or the scattering function, all of those would have error bars, and you would use the same formulas to calculate them, and they would be different. The fluctuations would be different, and the autocorrelation time would be different. I mean, you could get something like the energy, which would converge very quickly, have a short correlation time, but something like the structure factor, if something is undergoing a melting freezing transition, could have a much longer correlation time. It's possible, although unlikely. But yes, it's certainly true that every property you have to compute. This is why we have automatic routines to calculate error bars. So the general procedure is, I think in QMCPAC, isn't this right, John M? Correct me if I'm wrong, is you can dump out an observable to a file, and then you can come back later and compute the error bars on that quantity. And so you can dump out, say, 100 different estimators to a file, and then you can go in graphically and kind of look at them and look at the values and the error bars and so forth. Because each one would have, and you know, generally I was looking at the energy here, but if you're doing a simulation, like the path integral is a good case because you have ergodicity problems with path integrals, that you want to look at some key quantities to decide if your calculation is converged. You want to look at, I don't know, we used to, when Burkhardt was a student, we used to look at molecular hydrogen, atomic hydrogen transitions, and like the number of molecules in your calculation would be a thing that you might want to look at, and you might want to look at how it evolved from the beginning to the end of the calculation. And then that would have an autocorrelation time and an error. Any other questions?
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.